Welcome back, students, to the last lecture in nuclear physics. This is lecture 3, part 2, and in this lecture, we are going through the concept of nuclear fusion. So, contrary to nuclear fission, where heavier nuclei become lighter nuclei in the reaction, nuclear fission occurs when you have light nuclei that are less stable coming together to produce more stable, massive nuclei, right? And in the process, releasing energy. So we can also, again, just like for nuclear fission, explain why energy is released through using the concept of binding energy. We will say that energy released by this is released by this process because the average binding energy per nucleon of the product is greater than that of the reactants. So the products are more stable than the reactants, resulting in energy being released. So if we take a look at this diagram, this is a two-step fusion process, and this happens to be my favorite fusion reaction. So some people have a favorite color, some people have a favorite car. Mine is a favorite fusion process. So this is called the triple alpha process, and it's quite cute because it is two alpha particles coming together in a fusion reaction producing beryllium. One more alpha particle will collide with this beryllium in a second fusion reaction, producing the most important molecule to human life, carbon-12. Right? So we are all carbon-based life forms. Our proteins are made of carbon atoms. Our bodies are made of carbon atoms. Practically everything that we know that's organic is made of carbon-12 atoms. That's why it's called organic chemistry. So what's so special about this fusion reaction is this fusion reaction occurs in large stars, right? When larger stars run out of fuel, some of them will have enough heat and pressure to be able to cause this reaction to happen. And in this reaction, okay, it is very special because without this reaction, there won't be carbon in the universe. And it is special because this beryllium-8 nucleus that's produced in the first collision is actually not a stable nucleus, which means if this nucleus were any more unstable, it wouldn't last long enough for it to have time to collide with a third alpha particle, right? So you can imagine that there's some kind of equilibrium process where sometimes two alpha come together forming the beryllium, but the reverse reaction, which is the beryllium being unstable and decaying back into the two alpha particles, is possible. And this means that if beryllium always decays quickly, then we'll never have a chance to absorb another alpha particle to get carbon-12 nucleus, which we know is quite stable and common throughout the universe. So this is the nuclear reaction in stars that produces carbon. Right. Let's explain why nuclear fusion is possible and why it releases energy. So again, we will come to the binding energy per nucleon diagram. So on the y-axis, we have binding energy per nucleon. And on the x-axis, we have mass number. So this time we'll be focusing on the left side of the binding energy per nucleon graph. And you see that it's a lot more complicated than the almost smooth graph on the right-hand side for heavier nuclides. So we start with hydrogen. Now, hydrogen isn't particularly stable, right? But to make hydrogen into helium, we actually need protons to come together close enough for them to interact. And that's already difficult because they have electrostatic repulsion. Whereas for uranium, remember, we can just let it interact with a neutron, which is actually chargeless, right? So it doesn't have that problem. Now, to turn hydrogen into helium, we create alpha particle. And alpha particle is special because alpha particle is very, very stable. It is not the most stable element. In fact, it is still significantly less stable than iron. And it's actually also less stable than uranium because there is actually less binding energy per nucleon for helium. But helium is particularly stable for its mass. So for example, if you wanted to turn helium into lithium, you would actually require to input energy. Energy won't be released to turn helium into lithium, right? So lithium is actually less stable than helium. Probably has to do with the configuration of the protons and neutrons within the helium that makes it particularly stable. Now, after we get to helium, we need the triple alpha process to produce carbon, which is slightly more stable than helium. And then you have nitrogen and oxygen and fluorine and so on and so forth in a zigzag manner until you get to iron. right? So iron is the most stable element in the universe. So all these lighter elements will get more and more stable if we could perform nuclear fusion on them. Right, so reactions will tend to form in this direction with lighter reactants producing heavier products. So we can say that this part of the graph, the binding energy per nucleon against mass number, is steep. Right? So since it is steep, this means that any reaction would produce a lot of energy per nucleon compared to fission because it is more gentle. So of course, don't forget we are comparing per nucleon because this uranium nucleus has a lot of nucleons. So maybe his binding energy is very, very large. But then per nucleon wise, right, these reactions and fusion produce more energy per nucleon. So our qualifier is that although fusion reactions can produce a lot of energy, they are also very difficult to initiate because of electrical repulsion between positive nuclei when they are close to each other. So in order for this to happen, we need to set the conditions right. We need extremely high temperature, like about 100 million Kelvin, right? So that the particles have very large translational kinetic energy and overcome repulsion. So one possible pathway for fusion reaction involving deuterium is something like this. We'll take deuterium, which is the first isotope of hydrogen. Okay, it has 1 neutron and 1 proton, and react it with tritium, which is 1 proton and 2 neutrons, okay, in a nucleus, and reacting them together would produce a helium nucleus, which is our alpha particle, and helium is particularly stable, and an extra neutron is produced. This reaction produces about 3 MeV, right? But deuterium and tritium are basically helium gas. They're very light, so the energy per kilogram is way larger than fission. So if I could take 1 kilogram of deuterium and tritium and react them, I will produce a lot more energy than 1 kilogram of uranium. Now, the sun's energy source, okay, the sun is a main sequence star, so it's a source, or it requires a source of energy to keep it pumping, to keep it shining, right? And that source of energy is actually nuclear fission of something like this, but not exactly this. In fact, I showed you all the reaction earlier on in the last lecture, in the first page, right? That reaction is called the proton-proton chain. So although the triple alpha process is important in producing carbon, the proton-proton chain is actually also a very important reaction because all main sequence stars, basically stars that are burning hydrogen and producing helium, have this reaction in their cores. So this reaction is a chain reaction. It's not a chain reaction, it is a sequence of reactions, but not called a chain reaction. Okay, it's called a chain in that it requires a series of reactions to get from the first reactant to the last product. But on a whole, it's able to turn 4 protons, basically 4 hydrogen nucleus, which is plentiful in the universe, into an alpha particle, which is a helium nucleus. Okay, so stars are always in a state of flux, right? They are always having a desire to compress themselves ever so small to a smaller size because of the gravitational attraction between all the particles within the sun, right? Sun is so massive and it's made of some kind of gas, so obviously all it wants to do is just reduce this size. But if I can have sufficient heat within the system, I can oppose this, and we call this state of equilibrium hydrostatic equilibrium, where the star's internal pressure from its heat holds it up from its gravitational collapse. So a star is able to keep this shape for a long period of time, and we call such stars that are doing this main sequence stars. And in the core, it is hot enough to produce a source of energy that keeps the internal pressure large to balance the gravity, right? So this process, okay, we will first have 2 alpha particles, okay, who have enough kinetic energy to interact with one another and undergo nuclear fusion. In this reaction, we are going to produce deuterium. And a beta particle, which is just a electron-like particle, in this case it's an anti-electron. We'll explain more at the end of the lecture if we do have time. And a neutrino, which is another type of particle which you don't learn about yet. In the next chapter you will learn about it. Okay, And the energy for this reaction is only 0.42 MeV. It's not that much, right, compared to our deuterium-tritium reaction earlier on. Now, this process is not very fast. But the next step, okay, happens very quickly. The deuterium is able to quickly combine with another hydrogen atom or nucleus to produce helium-3 and release a gamma ray. So this one produces 5.49 MeV of energy, so the energy will be split among the gamma ray and the kinetic energy of the helium nucleus. Then the helium nucleus will again perform fusion reaction with another helium nucleus, right, to produce helium-4, which is the stable isotope of helium, and there will be 2 extra protons produced in this process, and this process releases quite a lot of energy. It is 12.86 MeV. So this 3-step process happens, eventually converting 4 protons into 1 helium nucleus. So along the way, somehow magically, 2 neutrons are produced inside when there were once protons. So protons can become neutrons in collisions. So actually this step here was the one that produced the neutron. So one of the proton became a neutron, and at the same time, the proton and neutron are not the same charge. So we need to conserve charge. That's why the beta particle carries away positive charge. So we're still conserving charge in our reaction. So in all our reactions, we still must obey the 4 conservation laws. We must conserve the nucleon number. We must conserve the charge. Right? We must conserve momentum, and we must conserve mass energy. Right? So this is still obeying those requirements. Now, in a diagrammatic form, this is what your proton-proton chain looks like. On one side, we have the 2 hydrogen giving us deuterium, 2 hydrogen giving us deuterium. Okay, each of them will react with 1 more hydrogen producing helium-3, and 2 of the helium-3 will finally give me my stable alpha particle and releasing 2 protons back into the star. Right? So this is the process, and it can allow our star to shine brightly for billions of years. The rate at which the hydrogen is consumed depends on the temperature and pressure. So for larger stars larger than our sun, they tend to consume their fuel faster. And for smaller stars that are able to support this fusion reaction, they will be consuming at a slower rate. Okay, so once the core runs out of hydrogen to perform this reaction, then this reaction will have to stop, right? And the star will have to undergo changes. So like what will happen to our sun is it will start to bloat, okay, and become a red giant star, and that will be a next phase of the star's evolution. So if you're very interested in stellar evolution, that's an entire subject on itself. Okay, it is very, very dependent on the smallest particles in the universe, right? Hydrogen. Right? This is our triple alpha process. So in stars that are big enough, right, the temperature in the core can go even higher, right? And once the hydrogen runs out, it is going to perform this reaction where it will take the helium that was produced in the earlier reaction and make carbon. Then in another layer, if you run out of helium, the core can start taking the carbon and merging it with 1 more alpha particle to get 16, mass number 16, and so on and so forth. So if the star is massive enough, right, the outer layers might be able to support the previous chains of reaction. So for example, in a very, very massive star, we might slice it open and see some kind of onion ring structure like this, right? In an outer layer of the core, or in an outer layer of the star, it is hot enough for hydrogen to become helium, basically something like our proton-proton chain. Then in the next layer where hydrogen has already run out, it's actually taking the helium and producing oxygen. Yeah. So it's producing oxygen and carbon using the triple alpha process, right? There's also a CNO cycle. Okay, never mind. In a layer that has already run out of helium fuel, then it will take its carbon fuel to produce oxygen, sodium, neon, and magnesium by adding alpha particles, right? And in the next step is producing neon, taking neon and making oxygen and magnesium, and so on and so forth until you're producing heavier and heavier nuclides that you get into the core. And the last step that you can ever produce in nuclear fusion is taking silicon, okay, and getting iron. Now the problem with iron is you cannot make iron more stable, so you cannot release any more energy through fusion. So this iron gets deposited into the core, and once the core is so full of iron that it doesn't have enough nuclear reactions to support the gravity of the star will just collapse. Alright? And we get one of the most explosive forces in the universe, and we call that a supernova. So in 1054, Chinese astronomers observed such a event, okay, and it's actually pretty common in the universe to have a very, very large explosion from the collapse of a star that cannot support its own mass anymore, right? And this explosion will throw off the layers of gas that has been produced in the star. See all this material here? These are all material that we find in the universe, right? These are all the different elements. And it throws these clouds of gas throughout the universe, and eventually some of these gas clouds may form a new star like our sun, whose solar system will now have more elements than hydrogen and helium. So for this particular supernova, okay, the one that was discovered by the Chinese, later on in 1731, the English astronomer observed a nebula, the cloud of gas. So it's called the Crab Nebula, and it's a very, very famous picture. It looks like this. So this is the Crab Nebula. So at its center, I think there's a neutron star. Basically, it's a leftover of the core of the star that has imploded on itself and thrown all its gas layers out. And this is a very, very famous photograph. So it actually shows us how the evolution of a star takes time, but in its final moments, it happens rather quickly. And this material will be then spread through the universe, creating the material for life. So back on Earth, things are a little bit more boring. So human beings, we want to produce energy. So again, we'll think of taking fusion reactors, turning them offline, and start making fusion reactors, since fusion reactors are more efficient, right? But it seems like we haven't solved this problem yet. Okay, there are a few ways we can perform fusion on Earth. So these are possible fusion pathways using isotopes of hydrogen, right? So these are all deuterium reactions. And in this last reaction, it's the one that we looked at earlier on, where you had deuterium and tritium producing helium. Right, so they each have different amount of energy released and different products of their reaction. So to perform nuclear fusion on Earth, okay, firstly we must have a temperature that's hot enough to allow for these nucleus to interact and undergo nuclear fusion. Right? So this requires like 100 to 200 million Kelvin. We need to get these guys, the ions, to be confined together in close proximity to fuse. Right? So the density required is something like 2 to 3 times 10 to the power of 20 ions per meter cube. That's very, very, very dense. And lastly, they must be held at close proximity for a long enough time so that they don't cool down. Something like for 1 second or 2 seconds. Right? So all these together make a difficult challenge, and if you want to make a nuclear fusion reaction, you have to have these conditions and set it up. So the most successful methods, I think, use a laser to focus these particles together and raise the heat and temperature and allow the reaction to happen. But I think it takes more energy to create the reaction than the actual energy release. It is not that the energy is not exothermic, but to create the conditions required for their release is not self-sustaining yet. So let's take a look at a quick calculated example for nuclear fusion, and we will be able to calculate the energy released in the nuclear fusion process. So in this example, we have deuterium and tritium, and we're going to form helium. So first, we're going to determine the energy released in this process, and then we're going to determine the temperature required for the reaction to take place if the Ke of the reacting nuclides is 150 kilo electron volts. Okay, this is actually example 9.2 in your notes. So the masses of the different nuclides are stated here. So just like for nuclear fission, and for any other nuclear reaction for that matter, we will always treat it as a two-step process. First, I will calculate the amount of energy produced in breaking up the reactants. Then I will calculate the amount of energy released by forming the products and find the net energy released. However, since only the mass is given here, we will find the net loss in mass or the mass defect, then we will use Einstein's equation to check how much energy that's actually worth. So here we can take the mass of the reactants, subtract away the mass of the products. This gives us the net mass defect for one reaction, and that's actually the mass that has disappeared because the reactants are way more than the products. So we can then use Einstein's equation, delta mc squared, to calculate how much energy is this mass that has disappeared worth in energy. So this is 17.6 MeV. And this energy is actually dispersed into the kinetic energy of our products, which means this hydrogen, this helium nucleus or the alpha particle will have high Ke, and that's where the energy goes to. And high Ke alpha particles basically are just very hot particles, right? And the neutron also has some Ke. Okay, now the question says that for this reaction to take place, the reacting nuclides need to have 150 kilo electron volts of kinetic energy. So what's the temperature required? Well, if we just assume that the deuterium tritium nuclei, okay, are some kind of ideal gas, right? Which is true because they are just particles that are inside a container, right? So then they are an ideal gas. And the translational kinetic energy of ideal gas molecules is 3/2 kT per molecule. And this is fine because my nuclei don't have any other modes of excitation, like they can't do rotation about a bond that some of our molecules do. So this is just 3/2 kT. So they're like ideal gas. They're pretty close to ideal gas, right? Other than the fact that they have Coulomb repulsion. Okay, then the required temperature will be, I can put in the kinetic energy on the left hand side and find T. Right? And it turns out that I need a T value of 1 times 10 to the power of 9 Kelvin. That's really, really hot, because the center of our sun is several million Kelvin only, right? 20 million? Right. So okay, that's in your notes, alright? I remember I printed it in there. So this means that we need to get the temperature to be hotter than the core of the star, which is possible for us, right? It's just that we can't sustain this for a big area, a big amount of gas. And this is the challenge in producing nuclear reactions, right? Or nuclear fusion reactions on Earth. So how do we overcome this problem? Well, we can look at some designs here. Now we're requiring to make molecules that are behaving at that are of the temperature of 10 to the power of 9 kelvins. So clearly you can't put it in any old bottle, right? Because you wouldn't be able to have a container that's able to touch such molecules and not vaporize instantaneously. So what you do have is you can use magnetic and electric fields to control the path of these molecules, or these atoms and nucleus, so that they never ever touch the side of a wall, right? So something like this, we have the plasma, which is actually just all these nuclei, right? They all don't have electrons, so they're just all charged particles. We call them plasma, and we blanket them in vacuum, so they're not actually touching anything. And then we will use magnets and electric fields to control their motion in a toroid shape, okay, like a donut. And then when we want them to have nuclear reaction, we just mash them together in the center, and then, yeah, that's basically the idea of magnetic confinement of plasma. And this type of reactor design is called a tokamak reactor, right? So in this reaction, the reactants never actually touch the edge of the container when they're hot. Alright, so this is the conclusion of fusion reactions. Now sometimes in A-level questions, right, they talk about a type of fusion reaction called pair annihilation. So I will go through a more difficult concept, but I think that this actually belongs into the realm of enrichment really. So if you're already overwhelmed at this stage with your content, this is a good time to stop. You can try your tutorial questions and wait for class and clarify any questions you have with me or your teacher. But if you're willing to listen for a little while more, let's talk about antimatter, then we can understand about pair production. So we have discussed a lot of types of charged particles, electrons, and in the nucleus we have protons and neutrons, right? So it turns out there's a class of particles that are like matter that we know, electrons, protons, and neutrons, but they are like the opposite. The opposite in the sense that whenever I get the antiparticle of a particle that I already know, it has the opposite charge. So for example, I can have an electron, which has negative charge, negative E of charge. A positron, which is the anti-electron, will have a positive charge instead of a negative charge. And of course, if I have a positive electron, I can also have the antiparticle of a proton, which is called an antiproton, and it would have negative charge. So of course I can combine the two of them together to make something called antihydrogen, which is like hydrogen but made of antimatter. So this is a big problem for physics because we have made antimatter in particle collisions before. We can use magnetic fields to check the mass and charge of those particles, something like a velocity selector. Right? And we use this symbol bar on top to denote that it's the antiparticle. Then why don't we see these antiparticles in our universe everywhere around us, other than producing them from nuclear reactions? Well, it turns out that our universe is made of matter and not antimatter, so that's a problem to be solved. We don't really fully understand why there is more matter than antimatter in the universe, but somehow or another, the universe is now made of matter, and none of it is antimatter except in very, very tiny amounts from collisions. Right. But we have been able to produce them, and we have observed them being produced in natural reactions. So what happens when an antiparticle meets its particle equivalent? They annihilate each other and both particles disappear. Right? And when they're destroyed, all of that mass that contained within the two particles will be converted to photon energy. So two gamma particles will be produced in a pair annihilation. So I will leave it to you all to discuss with each other and figure out why you need to have at least two photons. You can't produce just one photon. You always need two photons. Okay? The hint is that it's one of the conservation laws that we have talked about, the 4 conservation laws. Now, let's check our pair annihilation reaction that it obeys our conservation laws. Number 1, let's look at charge. The proton's charge is 1. The antiproton's charge is -1. So they cancel each other out. There's net 0 charge on the left-hand side. Now my photon obviously is uncharged, so it also has no charge. So charge-wise, okay. Now let's look at nucleon number, right? The proton has 1 nucleon number. The antiproton is considered to have -1 nucleon number because it's made of antiparticles. So the 1 and -1 cancel. So that's why we can produce 2 gamma without saying, oh, the nucleon number doesn't balance. Right? So this is an example of a pair annihilation. You can have pair annihilation for positron electron as well. You can have pair annihilation for an entire nucleus, like say a antiproton and an antineutron cancelling out another proton and neutron. So neutrons and antineutrons can also have pair annihilation. Alright, any particle can always have pair annihilation with its antiparticle. So all of the known universe is made up of matter, and this unsolved problem is called asymmetry of matter-antimatter. Right, so this is the one for electrons and positrons. So this is called a positron. It is an electron but with positive charge, and the normal electrons like this, right, with -1 charge. Okay, you might be wondering, then what about mass, Mr. J? So for mass, antiparticles still have positive mass. So as of yet, we don't have negative mass. The antiparticles still have normal mass. So if I could create a pyramid out of antiparticles, like create an antimatter pyramid, it would still be massive, right? It has mass. It's just that it is made of antiparticles. So if you want to look at what's inside the nucleus, what's inside the protons and neutrons that are inside the nucleus, we find that we can even find more basic particles. Now we're here at this moment in the lecture, we are really in the realm of particle physics, so this is not in syllabus for sure, but it's nice to understand if you want to listen. So within the nucleus, we have quarks. So within a proton, we have what we call an up quark, and a down quark. Now doesn't the proton already just have 1 electronic charge, E? Isn't that the least amount of charge that a particle can have? So it turns out no, because there's 3 particles here. So their charge is third fractions of charge. For example, the U quark has 2/3 charge, and the D quark has -1/3 charge. So that's why my 2/3 plus 2/3 minus 1/3 gives me 1 charge, 1 E of charge. And of course, the antiproton is just simply made up of an anti-up quark, anti-up quark, anti-down quark. And my neutron will also be made up of quarks. But in this case, the neutron has 2 down quarks and 1 up quark, so that the net charge is 0. So we have found heavier quarks that don't exist, they are unstable in this universe because we are at a different energy regime. So we have strange and charm quarks, top and bottom quarks, which are like up and down quarks, but they have more mass. Okay, so pretty interesting array of particles. So when I start to combine different quarks together, for example, I can have a meson, a pi meson in this case, which is just an up quark and an anti-down quark put together, or a down quark and an anti-strange quark, we get a kaon, and this is called the I can't remember the name of this already, but it's a quark and an anti-quark in a meson, right? Okay, I can't remember the name of this type of particles. So there was a period of time where we were able to make more and more and more weird particles by colliding more particles together and in nuclear reactions to get lots of particles. So it was a period of time that was so weird. We were just discovering so many new particles, and scientists were wondering, okay, how do we handle this? So it was like chemistry, right? You have so many different elements. In particle physics, we have so many different particles, which are elementary, right? We started to try to organize them into a model. Right? Okay, so in addition to all of this, where all these are just like things like protons and neutrons, right? We also have electrons. So electrons, okay, can have heavier versions. So this is called the muon. The muon is a heavier mass electron, and a tauon. And a tauon is a heavier mass muon. That's why we call them fat electrons. So we have 3 families of electron-like particles and 3 families of quarks. Up, down, 1 family, strange charm, 1 family, top, bottom, 1 family. So there's similarities among them. So we started to group up their similarities. So these type of particles, we call them leptons, things that are electron-like, right? They all contain E of charge. Okay, each lepton is associated with a neutrino, which has no charge and almost no mass. And we start to put them and classify them down into a diagram. So we end up with what we call one of the most important physics concepts, which is called the Standard Model. This Standard Model arranges matter into 3 generations. So the generation that exists and is stable in our universe right now is generation 1, where we have up quarks, down quarks, electrons, and electron neutrinos, right? And this model is actually, we think it's complete with the addition of something called the Higgs boson, which gives all of these mass. So the Higgs boson was the reason why we built the Large Hadron Collider, which your teacher might have mentioned. And the Higgs boson was discovered after I left university, which was a very exciting time for particle physics. So these particles here, you will notice that one is the photon, which you are familiar with, a gluon, the particle that binds the quarks together in the nucleus, in a proton and neutron, and both Z and W bosons, which govern radioactivity, which we will learn which you might come across in the next topic. Probably not. Okay, so we're approaching the last part of this lecture already, so apologies to tire you out, but if you really love physics, right, I think this actually makes you more energized, as you can see that I am. It turns out that particle physics, although it's at the forefront of physics right now, there are still many mysteries to solve, and there's room for young physicists to, do something basically. And these are 4 big problems in the universe right now. So number 1, we can talk about the matter-antimatter asymmetry, which is, why is this universe made of matter and not antimatter, and where did all the antimatter go? Is there a good reason why there's more matter than antimatter? Right, so this is one mystery. Now, we are familiar with 3 space dimensions and 1 time dimension, but are there more? Are they so small that we can't see them? Or are they so large and dilute that we can't feel them too? So are there extra dimensions? The other 2 is the basis of what makes up the universe. So dark matter. First is dark matter. We know dark matter is matter that is not like the rest of the matter that we know of that interacts with electromagnetic radiation, but it does have mass, so we can measure them, but we still don't know what they're made of because we can't interact with them, right? And we do know that it makes up a large portion of the universe. In fact, normal matter makes up only 3% of the universe, and antimatter makes up a good 20 to 30%. I can't remember the exact numbers. Alright, and we have also measured galaxies and found that galaxies are moving away from each other at an increasing rate. So the universe is accelerating in its expansion. Right? And what's causing that? We think it's something called dark energy, totally unrelated to dark matter. So dark energy is accelerating the universe's expansion. So what is it? Right? Where did it come from? Why is it there? All mysteries for us to solve. So plenty of chance to solve physics problems if you are interested. Now this is the end of the lecture, so do email me if you have any questions regarding the content that has been discovered. I've also left a summary in your notes for you to do recap. So do try the tutorial questions, and thank you for your attention.